Pyramids. What am I saying prisons? Prisons are easy. Pyramids. Pyramids. All right, now let's take a look at a really exotic pyramid. This pyramid is pretty cool. Check this out and tell me what you think. I think you might enjoy this. All right, now here, the base of the pyramid is actually a trapezoid. So this is given. This is all given to us now. So in fact, the base is a trapezoid, which I remind you means that this side is parallel to this side. We're told that this length is 8, this length is 5, and this height here is 4. And we're also given something else. This is a perspective drawing of this crazy thing. But we're told that this segment AE, do you see that segment right there? That's actually perpendicular to the floor. So it's actually perpendicular to ABCD, the plane that contains all those points, which I'm thinking of as the floor. So basically, AE is sticking straight up like this. Straight up. So really, this is a right angle, and this is a right angle. Why is that relevant? It's relevant because this thing is plainly a pyramid. What's its height? Well, to compute its height, all you do is you go to the very tip top and you draw a perpendicular down to the floor. But we now know what that perpendicular is. That perpendicular is, in fact, AE. And we're given that that length is 10. So the height of this thing is 10. So how do we find the volume? The volume is 1/3 the area of the base times the height. Now, how do we find the area of the base? Well, the area of the base actually is not too hard. Now, you might say, boy, I don't know what the formula is for the area of the base. But if you think about it for a second, you absolutely can figure this out. Let me tell you how I think about it, and then I'll show you the formula. Look, this is almost a rectangle, right? It's not quite, but it's almost. All I've got to do is take this length and that length and average them. If I were to average them, in fact, let me draw you a little picture of this so you can see this live. If I were to average these two lengths, that would fall right in the middle. And look what happens if I were to make a rectangle. Do you see this little surplus here? That would fill in exactly into here because these are congruent triangles. And similarly, this little teeny surplus here would fill in perfectly there. So this rectangle has the exact same area as the original trapezoid because this little piece here can be moved down to here, and this little piece here can move down to here. So, to find the area of a trapezoid, it's almost a rectangle. We just take the average value of this length and that length and multiply by the height. Base times height. Now, how do you write that down for real if you want a formula for it? I would never memorize the formula, but here it is. It's the sum of the two lengths of the parallel sides divided by 2, that's the average part, times the height. In any case, we can now figure it out. So here we go. So the volume of the whole thing is 1/3 the area of the base. The area of the base, we take the average of these two values, 8 and 5. So we take 8 and 5, we add them together, we get 13. We divide by 2, and so we see 13 over 2 times the height, which is 4. So that's the area of the base. Then we multiply that by the height of the pyramid, which, since we're given this very special pyramid, we know the height is the same thing as this length, which is 10. So I put all this together, and what do I see? Well, I can simplify a little bit here. I can see this is just a 2, and so I see a 2 times 13 is 26, times 10 is 260, divided by 3. That is the volume. What are the units? The units are centimeters cubed. Isn't that great? It's so much fun. So even the exotic objects can, in fact, have a volume that we can find ourselves. Cool. Little different. So let's find the volume of a cone with a base circumference of 18 pi and a height 6 centimeters less than twice the radius. Lots of words here. what's the first thing I would do? Draw a picture. I don't care if the picture's accurate or not. I just want something to be able to hinge my thinking on. So here we go. So here I have a cone. And I'm told that it has a base circumference. So I'm not given the radius, but I'm told that the circumference is equal to 18 pi. But I know the formula for circumference. It equals 2 pi r. So if I divide both sides by 2 pi, I see that 9 equals r. So they are telling me that the radius is 9, but in a sneaky way. So I go from the circumference information to the radius. That's good. Deny the radius. And what's the height? Well, the height, I'm told, a height 6 centimeters less than twice the radius. So I take twice the radius, and then I subtract 6. And so what do I get? Well, here I see 18, and 18 minus 6 is 12. Okay, so that was a very fancy way of saying the height is 12. Now I've got all the information that I need. I can actually compute the volume now directly. It's 1/3 pi r squared, which is 81 times 12. And if we simplify, we see 324 pi, and the units are centimeters cubed. No problem. So even when the information is camouflaged, our first task is to actually find the radius and find the height, and then we can use the formula for the volume of a cone to find its volume. One of the themes that we've been exploring is the impact on volume if we take each linear dimension and multiply it by some number. What I want us to take a look at is this pyramid, and I want us to compute the volume of the pyramid as it is, and then let's imagine that we take each linear dimension, so this length, that length, and the height, and we actually multiply each of those dimensions by a half. And let's see what the impact is on the volume and see what we can conclude. Okay, neat. Let's get going. So how do you find the volume of a pyramid? Well, we know what it is. It's 1/3 the area of the base times the height. So what's the area of the base? It's going to be 18 times 10, which is going... Oh, this is, by the way, I should say, we're given something. I apologize. We're given the fact that this is a rectangular pyramid. So, in fact, this is a rectangle. That's important because that's the only way we know for sure that we can take the 18 times the 10 to produce the area of the base. So we're given that it's... And it says that there, but I just forgot to say it. 18 times 10 is 180 times the height. And so what does that work out to be? Well, it works out to be, if we simplify this, we get a 2, and so I get 360. The units are feet cubed. Okay, but the focus is on 360. Now, or you can focus on this too, same number. Now, let's take each of these values and now divide by 2. So this becomes a 3, this becomes a 9, and this becomes a 5. And I want us now to compute the volume of this smaller object. Well, what's it going to be? It's going to be 1/3, and I'm going to write it out. Okay, base times height, that's going to be 18 over 2 times 10 over 2. And so that's the area of the base. Now times the height, it's going to be times 6 over 2. Now look at all those over 2's. Those over 2's are what? 2 times 2 times 2, that's 8. So I see a 1/8 out in front times the 1/3, and this gives me a 180 times 6. And look what you see. What we see is this piece right here is exactly the same as what we had originally, the original volume. So we take the original volume and we multiply by 1/8. Now, if you actually want the exact value, this works out to be 45, but that's kind of not the point. The point is, what's the impact? The impact is that when we change each of these linear dimensions by multiplying by a half, when we find volume, which remember is always, units cubed, then we have a half times a half times a half as the new scale factor. A half times a half times a half is an eighth. And that's exactly what we're seeing here. So if we change each linear dimension by a factor of 1/2, then the volume changes by a factor of 1/8. Again, we see the same principle recurring as a common theme. Neat.